Great. Yes, well, let's get started. Delighted that you all are here at Welcome today. We are honored to have one of the preeminent researchers on active galactic nuclei and quasars in this country, Xiohui from the University of Arizona joining us today. Xiohui is one of the Regents professors at the University of Arizona at Stewart Observatory. He is have so many awards, it's hard to list them all, including the Sloan, the Packard, the Guggenheim Fellowship. He is the discoverer of some of the highest redshift quasars, redshift lens quasar system, and has done just numerous projects on these extreme sources throughout his career. Xiohui is going to tell us about his work now with JWST and in this talk about quasars and the intergalactic medium cosmic dawn. All right, please, Xiohui.
Thank you. Great to be here and on Halloween night. So see some platform. And good to see a lot of people that I think I know many people here, and it's great to be here for a time actually. So today I'm going to talk about two things. The first part is basically sort of a summary of what we know about high-redshift quasars before JWST launched. And that is based on a review paper that I wrote with Eduardo Granados and Rob Simcoe last year. We wrote it because we basically want to set the stage of what we know about quasars before JWST, because we know that they're going to change a lot of things. So the second part, we're going to just show some of the cycle one JWST results that give you a flavor of what we think are things to come. So the cycle one JWST stuff really have a lot of contribution from Jinyi Yang and Pei Guang, two of the staff at Arizona who led a lot of the works I'm going to present today. All right, so before we go there, it's been 6 decades since the discovery of quasars, of course, by Barney Schmidt in 1963. The very first quasar was 3C273, which is a redshift a little bit more than 0.1. So at that time, it's sort of the cosmic frontier is a redshift 0.1, 0.2, right? And since then, as we go to higher and higher redshift, quasar has been really pushing this cosmic frontier. I think one way to set the stage of what is going on is I like to show this plot to sort of orientate what quasar, at least luminous quasar, is about. This is basically like a two-dimensional presentation of a few 100,000 spectra from one of the SDSS data released a few years ago, and you just put the one-dimensional spectra and order them by redshift and put them on top of each other. So of course, what you see are the mission lines sort of march through the wavelines from blue to red as redshift increases from redshift 0. This case, redshift 5 also. A few things to point out. One is you have the impression that the spectrum look very smooth. Sort of things are, except for their shifting in wavelengths, things don't seem to change very much. In other words, quasars look astonishingly similar at different cosmic epochs. We'll come back to talk about that, what that means for where the first quasars are, when the first supermassive black hole formed. And the second point is that the y-axis is basically a number count. And what you see here is that high-redshift quasars are rare. There are not many quasars very high redshift. In other words, we are a redshift higher than 4 or 5, approaching the epoch when sort of quasar population just began to grow in the universe. At the same time, the third point is that on the blue side of the landmark emission line, you see things get darker. That's because of the intergalactic absorption from neutral hydrogen begin to kick in. So landmark absorption that you see along the side. So as we're going to higher redshift, neutral hydrogen content in the intergalactic medium begin to change as we're approaching so-called epoch reionization. So today's talk, we're going to go beyond this plot, only talk about things that redshift higher than 5, sort of the first big year or so in the cosmic history. But this point I just made about the non-evolution of quasar spectra, the rapid evolution of density and the rapid evolution of intergalactic medium are still the basic message I'm going to talk about. So like 15, 20 years ago, we started finding quasars at redshift higher than 6. This is a paper, the last review we wrote in 2006. These are all the spectra of quasar redshift 6 also sort of close to the epoch reionization that we had at that point. What you see here compared to the last plot is this complete sort of lack of emission on the blue side of the landmark emission line. In other words, the IGM become completely opaque to landmark transition as we are approaching the epoch reionization. That is state of art 15, 20 years ago. And so when we wanted to sort of summarize what's going on in quasars in the last 15, 20 years, we want to remake this plot, but there are a lot more quasars that have been discovered at even higher redshift. So it's a bit harder to plot it this way. I don't know what it looked like. So instead, we did these two-dimensional presentation of the plot now with only quasars at redshift higher than about 5.3. So at this point, there are more than 1,000 quasars at redshift higher than 5, 200 also at higher than 6, and about 10 quasars at redshift higher than 7. So what you see here is the highest redshift quasar is right on here at redshift 7.6. And the same thing. So these are emission lines, not only MARPA, but also other emission lines. You can still see it all the way to the highest redshift. And on the blue side, you can clearly see sort of the universe is going from very opaque at those redshift 6.5 or above 6, to more and more transitions when you go to lower redshift. The universe sort of just moving out of the optical thick stage of the reionization. Yeah.
I just want to clarify. So these are like stacked spectra.
These are basically one line is one spectrum, and you just plot them on top of each other. So you see the line just moving.
And this is like actual observations, or is this like models?
These are the 1,000 quasars.
Okay.
These are every single spectrum we can find in the literature, and we just put them together. Yeah. All right, so that is the sort of state of art of the quasar survey. But the question we want to ask is actually a quite old one. It's basically how supermassive black hole form. We're now looking at supermassive black hole within the first few 100 million years of the cosmic history. And the question has been asked for almost half century now about what is the pathway of going from the initial collapse of module gas cloud to the supermassive black hole. So I'm going to go look at some of the pathways later, and also the recognition that in order to understand as a sort of the point made by Martin Rees in one of the classic review papers he wrote, that in order to understand galaxy formation, you actually quasar or active galactic nuclei had to be an integral part of it. And I think the goal of this talk really is to talk about how quasars are early galaxy formation are connected. One argues they are actually connected in many different spatial scales, from all the way from the smallest scale, which is the scale of the black hole in sort of the accretion disk emission line region, very close to the central black hole. And we can observe the properties of AGN there to probe how massive they are, how fast they're accreting. Move a few order of magnitude bigger to the scale of galaxies. We want to see what kind of host galaxies these quasars are living in, and whether they have some kind of interactions or feedback that make the galaxy and quasars go together. And then finally, a larger scale on the megaparsec, tens or 100 megaparsec scale, of course, these quasars are powerful probe of the reionization through looking at absorption that you saw earlier. Today, I'm mostly going to talk about these scales, and I'm going to skip reionization, I think, just for the sake of time. All right, so I said there are a lot of quasars now. This is sort of a summary of all the quasars like we know until last year. And you can see their distribution in redshift versus luminosity, and these different shaded point regions are basically the surveys that people have been using in the last 2 decades to look for them, from initially slow digital sky surveys that many of us have been using for 2 decades, the pan-stars to things like DES, and then finally when you go to redshift higher than 7 also, because the lemma alpha is moving to the infrared wavelengths now, you have to use sort of near infrared based surveys to look for them. And you can see the number of this is quasars at redshift higher than 5.3. The reason we picked 5.3 as sort of a redshift threshold is because that is the redshift that people think more or less the reionization finally stopped, or the last piece of the sort of intergalactic medium getting around that. So this is really sort of reionization era quasars. You can see the number of optic increases as function of years just because of collection of these surveys. I want to highlight 3 objects that are sort of give you a flavor on the objects we're looking at. these are the three quasars I want to talk about. The first one is this one. This one is really bright. This one is object that is redshift 6.5 and the absolute magnitude of -29. Or you think about sort of the apparent magnitude is like 18, 19 magnitude, the redshift 7-ish. That's just bright, right? So turns out this object is not because it's intrinsically luminous, or it's quite luminous, but really because it's boosted by gravitational lensing. This is the most distant lens quasar that we discovered a few years ago. And you can see it's a very weird lens. Well, you can see it from the HST image. It's not your typical quad or double that you see. It's actually a triple lens system with a galaxy sort of in the middle. It's a more or less adjunct galaxy that cuts through. And then sort of this configuration gives you a very large magnification, a very, very compact lens configuration. The magnification is about a factor of 50. And because the object is so bright, it's actually brightest thing in the early universe in terms of its apparent magnitude, all the way from X-ray to submillimeter, and any wavelength is the brightest. And that what that allow you is actually to do interesting galaxy science with it. There are many lines that ALMA can see, for example, to look at all these different transitions from atomic molecular lines. And then the other thing that ALMA can do is actually, you can see here is resolving the host galaxy to a giant arc. And naturally, we haven't quite finished analysis of a high resolution ALMA image, which we think actually because of this landing effects is the spatial resolution is of the order of about 50 to 100 parsecs, the redshift 7. So you can actually go in sort of inside the black hole sphere of influence to see what kind of gas motion is there very, very close to black hole there. You can see there's a very strong velocity gradient. Actually, when you see the high resolution image, I didn't have it here. There's clear sort of velocity shear right in the middle. Whether that is the covariant motion people are looking for, we don't quite know yet. But these are the power of sort of the combination of natural telescope with the highest resolution ground-based telescope actually probe the environment of these quasars very, very close by. The second object on that plot is, I think is that object, the redshift 7.5. This object, which was published like right before the pandemic started, is a redshift 7.5 quasar. Is the first quasar we know at redshift higher than 7 that contain a billion solar mass black hole. The way that people determine black hole masses for these quasars is so-called scaling relation. Yuya is an expert in that. Basically, you're measuring the line width of things like median to H beta, and assuming that this line width is caused by some kind of gravitational velocity, and then use some kind of scaling relation to scale the luminosity of the object, size of the ball line regions, and sort of V square R to get a mass. So this is the first object, the billion solar mass, also a redshift higher than 7 also. And the object has a nice Hawaiian name, which I don't want to pronounce it, I'm going to screw up. It was because it was discovered in Gemini. Sort of one of the things that we do is actually to work with basically school teachers in that Gemini or the Hawaiian community is working with the school teachers here to come up with names. You may remember some of the names that M87 had the Hawaiian name as well. This is the first legitimate quasar that M87, the dead quasar. This is a real active quasar that actually got a Hawaiian name because of it's discovered in Hawaii. So the second object. The third object on the plot is the most distant quasar, redshift 7.6. This object was actually discovered we didn't know that, for the very last run before everything shut down. And the object was observed at Magellan Telescope. I was there observing it. Well, basically, I had a strict order from Figo, my colleague, saying that you have to observe this object no matter what tonight. And we didn't know that. We didn't go back to the telescope for another 3 years, obviously. It was just a luck that we got this object right before the cloud came in and turns out to be the highest redshift quasar. The thing interesting I want to point out, this object is not only quasar with high redshift, but look at the spectrum of this object. Compared to the blue one is sort of a more or less matching template without the intrinsic spectrum supposed to be based on longer wavelengths emission. You can see there are a lot of absorptions here and here. These are basically outflows from both absorption line features, basically winds from the disk tells you that they are outflow material even at the highest redshift. Actually, the fraction of this kind of object is higher at the highest redshift. In other words, at those epochs, the quasars already begin to do something to its surroundings, interstellar and circumstellar medium around them. So these are three quasars that sort of highlight the stream at that epoch. Each of them carry out some sort of interesting messages. But before we move on to talk about quasars' connection to galaxies, I want to say one more thing about sort of where we go from here. In other words, how high can you go in terms of these survey for these luminous quasars? The quasar density is extremely low at that point. You can see this is the unit of per cubic gigaparsec. In other words, we're talking about less than one object per cubic gigaparsec at that point. Gigaparsec size is like the largest cosmological simulation you make these days. Is of that order. So these are extremely rare objects. And if you just extrapolate the evolution of number density of these luminous quasars to arbitrarily high redshift, and that's the question, like at which point you get one object over the entire sky, then you're done, I guess. That object is sort of, for these luminous objects, is redshift 9 or 10 or so. In other words, by then, we can claim that we have found sort of at least the first few of the billion solar mass active billion solar mass black holes in the universe, unless there's some kind of weird selection path or something.
So obviously, quasars are going to be, even a smaller fraction here. And so would it be reasonable to say, for example, that the blazar recently found at 6.1 might be the highest redshift quasar? Is that ridiculous or?
No, it's not, because we are looking at all sky surveys more or less these point. So for luminous quasars, the limitation is the infrared observation is not quite sensitive enough, and the blazars is only a fraction, like a few percent of the quasar population, because they are the thing that haven't point towards you. So you are getting pretty close to that. We don't need deep infrared observation to find them. So they are getting very close to, we're done. Yeah.
How does that extrapolate down to the higher redshifts?
Or just draw a line from the low redshift. Yeah, I just sort of. Yeah, there's no physics in it. There's no physics. We're just draw a line. Who knows what the line is supposed to be? But the point is that you're getting pretty close to find these rare objects in the universe. And the way to find them, of course, is the next generation survey. Euclid just can launch. Roman will be launched soon, and hopefully JWST is going to work in the next year or so. The combination of these surveys will allow you to find these rare quasars in the next decade. I think follow them up and try to identify them actually not trivial as well. Okay, so now let's talk about sort of connection to galaxy formation in the different scales. I'm going to go very quickly because I want to get to the JWST part. So in terms of the black hole mass, just sort of recap what we know. This is a collection of all the black hole masses we have a redshift higher than 6.5 or so. We can see that the black hole mass sort of for luminous quasars range from 10 to the 8 to 10 to the 10 solar masses. And actually, there is an object that we're still not quite sure what the real black hole mass is, because the object looks reddened, so we don't quite know the luminosity. So there's probably a lower limit of about 10 to 10 solar masses, redshift about 7. So there are 10 to the 10 sort of billion to 10 billion solar mass black holes really exist at that point. And the other method is that the way that we measure black hole mass carry no information about whether how fast they're accreting or whether they're adding accretion or not. But on the other hand, when you plot them in the plane of black hole mass versus luminosity, this line is sort of adding the accretion. Simple, just simply Eddington rate. Even though theories tell me that there's no reason Eddington rate should exist, but they are still here. They're more or less, if these luminous quasars, you expect them to be accreting about as fast as they can, and turn out they are. Compared to the lower redshift contours, I think is from US work that seem to be at lower average Eddington rate. So they are massive, and they are accreting about as fast as you think they can, at least for when you observe them. And you will combine those. This is a typical argument people make, is you will combine the Eddington accretion rate with their mass, then quasar mass should be double every few tens of million years. Then you just extrapolate to higher redshifts to see where they land, sort of their initial collapse or initial seed. For these objects, we have billion solar mass, a redshift more than 7. Even if their seed started at redshift 30, the mass is going to be beyond what you can do with normal stellar evolution process, like collapse of massive stars of 100 solar masses. So you have to go to 10 to the 3 to 10 to the 4 solar masses to form them. Of course, if their seed is low, you have even lower redshift, then the constraint is even worse. This is probably not the whole story, but what that shows you, at least for these objects, is really hard to make them that early. So people like to begin to involve like more exotic physical process to form them. I mean, I think one of the things that I like to say is that we are really just seeing those redshifts, seeing sort of end product of the black hole evolution. They are basically fully mature, massive, luminous things, billion solar masses. And it's a long way to extrapolate. So to understand this picture, whether that's reasonable or not, you have to go somewhere in the middle to see what is going on in these objects. And that's sort of the first thing that will JWST come in. This is not my work, but the popular thing these days is a sort of new word called little red dots. These are objects that have a red color in the JWST color images, and many of them show broad emission lines at redshifts are between 5 and 10 that could be these sort of a much more less luminous AGN with much less massive black holes that fill in the gap between the seed and the 10 billion solar mass black hole that we see at redshift 7. That's something that I'm sure you'll be hearing a lot more in the coming years. And so, but our job, the goal of this talk is still focusing on the most massive ones. So whether these little red dots is sort of the intermediate product of this black hole world or not, I think we'll see in the next few years. I'm going to talk about the black hole galaxy co-evolution or JWST later, but let's just show something before JWST time. Is first of all, it's just impossible to do these kind of things even with Hubble Space Telescope for redshift 6, 7 Quasar host galaxy. Just some example of sort of pre JWST data from the best HST work you can do at redshift sort of 6-ish, and you just don't see anything. After you subtract out the point spread function from Quasar, you see a bunch of noise. That's pretty much because you're looking at UV, where the Quasar host galaxy is faint to begin with, and then this 1 + e⁴ power of surface brightness dimming is really killing it. So it's hard to do. So instead, people in the last 2 decades have been focusing on actually looking at much longer wavelengths, not looking at this part, the optical UV part of the Quasar emission, because this part is really the central AGN is dominating the light. That's why it's hard to detect the host galaxy. You're looking at this part, sort of the warm dust coming from the host galaxy, where the Quasar center is not dominating anymore. Even sort of the hot dust torus has become sort of fade in the Regin cell, and then you begin to pick up the dust and sort of dust continuum and atomic and molecular lines start tracing star formation and dust formation, dust emission in the host galaxy. Just some highlight of what people have been doing with, mostly really with ALMA. One is that, remember 20 years ago, we spent like days of observing time to observe 1 or 2 objects and try to detect them in sort of millimeter, sub-millimeter wavelengths. And with ALMA, you can pretty much detect most of the luminous quasars, host galaxies, dust emission, and as well the C+ line, sort of brightest atomic line in the quasars within like a few minutes for these objects. So these are very bright. I mean, by ALMA standard in terms of their dust emission, which tells you there are a lot of star formation in general. So ALMA sensitivity allows you to carry out sort of a quick surveys of these objects, and the resolution allow you to look at really detailed 100 parsec scale. I told you before that with landing, you can look at sub-100 parsec scale information. So the spatial resolution is comparable to JWST resolution, of course. And the thing I want to highlight are these 2 objects. These 2 objects basically, and I think I'm going to repeat this particular message many times in the next 20 minutes. These 2 objects are more or less indistinguishable in terms of what they look like in their reference optical UV spectrum. They have roughly the same stellar black hole mass, similar luminosity. They look similar as far as quasar goes, but their host galaxy in ALMA look very different. One of them is huge. There's a lot of sort of a random motion in it. Maybe there is some kind of cavity even in C+, who knows whether it's related to feedback or not, but it's a much bigger galaxy, much messier. The other objects, same kind of quasar, same redshift, look much more compact, with sort of kind of a strong velocity share that is being resolved, look like some kind of supported by rotation or something. So these are two extreme objects in those redshifts when you look at their host properties with ALMA. On average, these things are strong star formers. So basically, when you look at either their far infrared emission coming from the continuum, or look at their atomic line emission coming from C+, and sort of translate that into star formation rate, on average, with a very large range still, on average, it's sort of like peaked over at hundreds of solar mass per year in terms of star formation. So there are ultra-luminous infrared galaxies in general, those redshifts, but again, so the very large range of star formation rate, sort of from 10 to like 1,000 solar mass per year. When you look at the whole population, this word diversity come out again. On average, again, these things are relatively compact, few kind of 50 kiloparsec in terms of the half-life radius, relatively turbulence. All of them seem to have sort of large intrinsic line width. There's a lot of turbulent gas motion in it. Relative star formation rate with a large range. Their dynamic mass is massive, but again, with a large range. But when you look at the morphology, they sort of fall into three different kinds. They're about a third, maybe less than that, objects that look like the top one, that have a nice sort of velocity gradient that you can at least model them with some kind of rotation. Sometimes it's very hard to figure out whether they're really rotation or some outflow. But for certain, well, all they have been resolved with many resolution elements. They're very clear there's some kind of good, large scale velocity gradient in it that's consistent with rotation at least. About a third of them look like, or maybe more, look like the mass, look like some dispersion dominant systems, but still look compact and round. And another third kind of object look like object have close companions that have a disturbed morphology. So some of the objects look like merger or something like that. And some objects look like the object that maybe is forming some kind of bulge, just like think of the hand waving and think of what's going on. Some of them look like kind of settled down on some kind of star formation disk. So that's a diverse population we see in ALMA. We're going to look at JWST things in a minute. One message people like to talk about is that these things are overmassive in terms of their black hole masses. It's not clear, we know how to measure black hole mass, or at least order magnitude wise. It's not clear how to measure the host galaxy mass. So people use various kind of proxies to measure the black host galaxy mass, whether it is through the line width from the ALMA observations or some kind of dynamic modeling for a small number of objects that we can do that. Or more recently with JWST, people try to fit like stellar mass to it. But whichever way you want to plot the x-axis, velocity dispersion stellar mass with some kind of dynamic mass against the black hole mass and compare to the local relation, at least for all the quasars that we see, they're all about factor of 10 above the local relation for luminous quasars. And there's a combination of probably evolution of the thing with a lot of selection impact in the sense that we are really catching up we can only catch these very luminous quasars by definition, just because you see them, they are very massive black holes. So I'm not sure whether this is I'm sure it's not completely a evolution of M-sigma relation, but large part is because they're probably not very much of an M-sigma relation at that point, instead of their law of scatter of how fast you can grow a black hole versus how fast you can grow a galaxy. All right, so now let's talk about JWST. So I want to just highlight a few results that we have on the first a year or so of JWST's observations that we have. Talk a little bit about supermassive black holes, but mostly about host environment and sort of large scale structure that these quasars are living in. In cycle 1, JWST actually spent quite a bit of time on high-redshift quasar programs, and this is a sort of just tells you where these cycle 1 and cycle 2 didn't cycle 2 actually have a lot of sim quasars observed differently, but roughly the same sample, sort of beyond redshift 6 to highest redshift over a rather large luminosity range over a number of programs. I'm going to highlight 2 programs. The first program, both led by our group in Arizona. One program we call Aspire. This program is sort of 3 things in one. What we do is we want to look at supermassive black hole and feedback, galaxy properties, and quasar environment with one mode of observation and large sample. So here we want to get the optical emissions for the quasar itself, so the spectrum of quasar. Similarly, we want to carry out imaging to look at stellar light and continuum and companion galaxies. And then we want to carry out a spectroscopy survey of the whole quasar environment. The way we do that is we use the so-called sliver spectroscopy mode. So we're basically doing a imaging first in the same field. We put a prism in front of it to disperse all the light to get spectral of every object in the field. Of 25 quasars at redshift 6 or so with the near camps of the wide field spectroscopy mode. That's the sort of the gist of this Aspire program. One mode, 25 quasars. And of course, when we open up just no slit, everything, we're getting objects not only in the quasar environment, but also in the foreground background as well. We can measure redshift of them. So it's also basically a galaxy redshift sort of legacy survey that can do all kind of galaxy and science related to intergalactic and critical gas medium that I'm going to talk about today. So that's one approach, is one node, 25 quasar. The other large program, medium program that we led, it is sort of, we call it frontier program. This is basically look at only the 3 highest redshift 7.5 quasar with all the modes we can find. So these are 3 quasars with essentially all the observing modes that are relevant using JWST. I think I even missed one of the modes here, which is sort of a parallel thing. So we're using 4 instruments actually, and this just shows this one particular quasar. When we stitch up like all the spectral screens we have from near spectrum, there are near infrared wavelengths to mid infrared wavelengths, you can see HR. Yeah.
Just to make sure I'm following, both of these are targeting specific known objects.
Yeah, one of them targeting 25 quasars with one mode, 6 to 73 quasars with all the modes. Both of them are known quasars. Yes. So this is really a nice spectrum showing the power of JWST. Now we're talking about observed wavelengths of a few micron now, which is just impossible to do it before. And this is one of the highest redshift objects that you can actually, the highest redshift object, you can clearly see H alpha emission line it. All right, so now I'm going to highlight some of the early results coming from this combination of these 2 programs. The first thing is sort of the simplest thing is just to get a spectrum of objects. These are sort of the reference optical spectrum coming from the survey sample, H beta, and then octet 3 that. And you always see those 3 lines together. What you see here is that H beta typically is regarded as sort of the gold standard for measuring black hole mass, more reliable, more better calibrated. And what we compare is sort of the previously ground-based black hole mass determination from a median 2 with H beta. They're more or less okay. So that's not surprising, but nice to confirm that the H beta, the previous black hole mass measurement is at least consistent with the new one. What is more interesting is sort of the diversity of the spectrum here. They don't look like your typical textbook quasar spectrum. This one do. The other few objects look a little bit weird. This one doesn't have any octet to speak with. These bumps actually bumps coming from iron 2 emission in those quasars. Why there are a lot of iron there is another story at those redshift. These are redshift 7. And then you see these objects have really weird octet 2, broad, asymmetric, something else is going on. I'll show in a minute. So early black hole is confirmed, but there are clearly a lot of other things going on. Now move on to host galaxy, just sort of very quick highlight of what we have. This is the picture we want to see, right? So this is sort of the textbook quasar host galaxy image from old HSC observations of very low redshift objects. What you see here is that quasars living in all kinds of different things look like a little galaxy, look like a spiral, look like some kind of merger system and so on. As I said, we couldn't see that with HST for these redshift 5, 6, 7 quasars. However, we tried in the last 2 decades. Now we begin to see interesting things with this. So there's 3 examples. Of course, these are 3 good ones that really begin to show sort of some of the whole galaxy will have a lot of interesting things going on. This is a JWST versus ALMA, the same spatial scale. The first one is an object that after we subtract the PS, have a lot of stuff around it. And a lot of stuff is corresponding to some of the Lambda alpha emitter and some of the carbon 2 emitters that we see from Lambda alpha and from ALMA. These are stellar continuum, basically, optical continuum from stellar light. So this object happened to also be sitting in one of the largest protoclusters at high redshift. Almost make you feel like this is some kind of proto-brightest cluster galaxy, as a lot of things begin to merge together, because the object really sits in the middle of this much larger overdensity that we saw in high redshift. This object looked like clearly some kind of 2 galaxies begin to merge together, both in the stellar light and in dust continuum in ALMA. And then the third object is actually the biggest host galaxy that we see in JWST in terms of spatial scale, and also turned out to be in terms of the velocity map, show a very, very clear gradients of the velocity map as well, some kind of rotationally supported thing again. So finally, we're seeing host galaxies in these quasars. And not only that, we're seeing a diversity of them again. And what I didn't show you is the rest of the sample that some of them we don't see it. So again, these quasars are very, very similar in terms of their spectral properties as far as quasars is concerned, but their environment look like have a lot of different things going on. One exciting thing to begin to see is some indication of what the AGN the quasar is doing to the host galaxy. This is the spectrum that I showed you before again, with this rear obtaining 3 line, has some kind of blue shifted broad component in it. Turns out the blue shifted component is like over here, spatially extended offset from the quasar itself. In other words, this looks like some kind of outflow from the Alpine 3 line, which is usually regarded as a good tracer of the outflow coming from sort of the wind from the galaxy. And if you use sort of standard conversion from the sort of luminosity and the spatial scale and velocity scale of the thing, to convert that to some kind of a kinetic power, the power of this object is of the outflow is about a few percent, 10% of Eddington luminosity of the quasar itself. And that's comparable to this line of object, which is sort of the so-called extremely red quasars that a lot of them seem to have all outflows that could be affecting or blowing up the galaxy. A much higher kind of kinetic power than say more normal quasars at lower redshift. So that's just an example of, at least for some of the objects, there could be outflows that have enough power to suppress star formation in the host galaxy. So another example is a integral field unit spectroscopy for one of 7.5 quasars. This is like 10, 15 hours of time, just because things are faint, but we see now we can see a spatially resolved outflow from in terms of the flux, in terms of the velocity. So there's like 500,000 kilometers of the velocity that extend to a couple of kiloparsec away, with kind of a kinetic power very similar to the one that we had before. So we don't have statistics yet, but it's for some objects, they seem to have this signature outflow that we have been looking for a very long time. All right, so going to close up by looking at, I think it's actually the most exciting part of the program is actually to look for companion galaxies. And the way we do that is to use selective spectroscopies. So after the direct imaging, when you put dispersion in, of course, all the objects become aligned, become dispersed, become a spectrum. And for the quasar itself, you see the nice mission line. But for a lot of objects, after you get rid of the continuum, you just clean up the things that you begin to see these 3 things that are coming in sort of triplets, and that immediately tells you is a H beta oxygen 3 pair at the redshift we're looking for. And you know when you find cornerstone object you know the redshift. So this is an example of our project that worked a lot better than we thought. Basically, when you write proposals, you sort of try to be optimistic, right? Try to predict predict about as many objects you can predict. We turned out we under predicted how many galaxies we can see in those surveys by quite a bit. Because the early universe that you heard from JWST just like had more star formation in it. And JWST is a little bit more sensitive than actually the pre-flight numbers. And we're looking at really bright objects where any kind of sensitivity shift actually give you quite more objects. So this is our Aspire program with another few programs, either Quasar field or some random field, looking at this kind of same thing, slitless spectroscopy to look at large volume of galaxies. And this tells you that for our 20-ish systems, we have few hundred confirmed redshift. We're really doing redshift surveys at this point. And what you see here, for this part, you see a lot more galaxies right here. That's because they begin to bump into quasars. That's what we're looking for. We're looking for whether these quasars living in galaxies that have overdensity or not. And actually, this is the first field that we looked at. Turns out this field had a lot of galaxies and exactly redshift within a few hundred kilometers from the quasar. So clearly this object, this quasar is sitting in the middle, or actually sort of more like a linear structure you see here from one side to the other of a filament looking structure and exactly the same redshift traced by these emitters. So this kind of thing, again, we tried very hard to do. I mean, we means actually many different groups tried very hard on HSC for many years. And finally, with redshift, really, you can see this kind of structure. And when you look at all the quasars we have, the message is actually fairly mixed. These are just for all the different quasar fields, how many alternate emitters you see. The black line about 1 is what you're supposed to see, sort of calibrate all the random blank field with these other surveys. You're supposed to average 1 if quasar is not in overdense environment. Of course, these are very luminous quasars in the early universe. They're supposed to be in sort of my bias, very, very massive halos. Many of them have many galaxies, which means they are really in very dense environment, but not all of them. On average, they are, but again, you see this diversity as if the same kind of quasar with similar black hole mass, but the environment, some of them are not dense, some of them very dense, some of them may be living in very massive halos. You know, directionally that some of them may not be as much. But for the dense one, what you consistently see is actually a lot of them have this kind of a linear structure in it, so as if the early filament just begin to form at those points. Okay, so that's sort of a highlight of some of the early JWST results that we see. Now let's just give you sort of a few closing thoughts. One of them is, the first one is, I think we're getting close to the first very luminous quasars, redshift 9 or 10 also. But really to understand the whole picture of black hole growth, we want to go to fainter object and higher redshift, which is the job of JWST surveys and Roman surveys. The second is early quasars are living in fairly diverse environment. And I think the picture of sort of black hole feedback like killing the galaxy is quite a bit more complex than that. And the third point is that I think JWST is really showing the power of all different observing modes, especially JWST enable you to see the emergence of larger structure, whether in quasar field or not, and allow you to actually making sort of connections all the way from the black hole scale to make part scale larger structure at those early times. All right. Finishing. Thank you.
Lots of questions. I saw King first.
Do you have ALMA for those Aspire sources, those fields?
Yes, there is an ALMA large program that our target sort of the same kind of just tile mosaic of all the, I think most of the field and the program is done. So the observation relatively shallow. We see overdensities, but not quite as prominent as JWST do. And the other thing I think we see is in most cases, the Oakland emitters and C+ emitters are not the same. So I guess the obscured ones and unobscured ones.
And so like the ones where you don't have any companions, do you see anything in the signal emitter in those or?
I don't think so. I think they are, I think they are consistent.
Okay, so
I,
it's, they're correlated.
I think that's right, but I need to double check exactly which one is which, but I think they're more or less consistent.
I see a question from Stu online, and then we'll go to Gil. Stu, you should be able to unmute and ask your question.
Okay, thank you. Can you hear me?
Yes.
Two questions. One, as you know, there are many alternative models for forming the first black holes. Given what you've shown and the possibility that there might be black holes of redshift 10, the Eddington accretion story from stellar mass black holes doesn't look very promising. Alternatives, as the Reese plot showed, include galaxy cluster, stellar cluster collapse, dark matter cluster collapse, supermassive stars, etc. What's your favorite candidate for forming these massive black holes, 10 to the 4, 10 to the 5 solar mass at the earliest redshift? Do you have one?
I don't have one. I don't know. I mean, I don't know how this. I think one thing that I have to point out is that I think the story of these early luminous quasars is nice, but they are really rare objects. They are weirdos. They're really just monsters that somehow get there really fast. So whether that translates into a common like a mechanism of forming black hole is not clear to me. So the message I want to say a few times already is to look for fainter, more less massive objects, because these are more common things, maybe more sort of more general in terms of how things form. These objects, who knows how they're formed? They're just really, really weird. So I don't have a favorite theory, but I think one of the things that I like to believe is that there are a lot of obscured, very fast growth in the earlier in the earlier part of the growth, such as we just not sensitive to. No matter how their initial seeds formed, they probably creating. The accretion may happen in some kind of obscure fast phase, at least for part of the time.
Yes, super Eddington, maybe.
Right, yes.
Gil?
Thank you.
So related, can you just put that plot up again, the group? I always see it
So
down
what?
where everyone goes back into the past. What happens if I go that forward with that?
Well,
I mean,
hopefully they don't, right? So because we already get 10 to the 9 solar masses, they better not grow by much because we don't see them.
well, right, but why not?
Hopefully the outflow will kill them, but that's what we're looking for, right? To kill the star formation eventually.
Okay, but I mean, it can't go up much further.
No, yeah,
right?
I mean,
So-
yeah,
so
to
we're
give another few, I think that's probably the time scale, they're about the massive ever.
Right,
Yeah, so they have to stop, and we're really looking at things that barely are, I mean, I think again, the problem is we're looking at a multi-stream system. These are the systems that somehow allow them to grow that fast, but they are probably on the edge of not growing anymore. Otherwise, I mean, that just, otherwise we'll have seen them. Otherwise, we'll have seen 10 to 12 solar mass.
is there a physics limit? Or anyone has ever hypothesized?
I don't, I mean, in terms of, and some people growing black holes more like Kurt is more expert than me in terms of whether there's real limits.
You mean in terms of total mass or? Yeah, because there's a mass of the size of the halo and stuff.
Of course, of course, halo mass is a limit. You don't have enough thing to fill them anymore. But of course, 10 to 9 is still far from it.
I see one question from Ryan online.
Yeah, so I was just wondering about time variation. So for these really high redshift quasars, do you see time variation? Is there any information in that?
For these very luminous object, not very much. They're so big and the redshift is high enough. I don't think we are having a lot of variability. For lower luminosity objects, yes. I mean, we actually we were just comparing recently of something like a JWST data with something HST data and see things begin to vary for some of these things. Not for these quasars. These quasars, I don't think there's a strong evidence of time variation there. They're just too big.
So two questions. My first question is, What are the number densities of the billion solar mass quasars at redshift 7? Is it comparable to the number density of CD galaxies in the local universe?
I mean, they're lower.
Lower than
These
that.
things are lower than, I think you were talking about 3D galaxies, probably you need to go up to the curve a lot, because these are, I mean, for these, they are like Hubble volume kind of thing, one object, so yeah, they are rare. And these are the rarest peaks.
Okay.
They're not, the CD galaxies are not, these are like 6 sigma peaks. In you think about the Gaussian random field, so these are much rarer systems than even rich clusters. Whether they can grow in rich clusters, that's a different question, right? So I think the simulation show that they are in, all these objects are in massive system, but they are not the most massive system today. In other words, other things a late bloomer can catch up actually. I think that is simulation show that.
So somewhat related to this is since by number they are negligible compared to the population of supermassive black holes, of course, cosmic time. But you also mentioned that at early times, the host galaxy properties are so different from the Bacow et al. Results at nearby universe. I was wondering what's going on at redshift 4 and 5? What are the host galaxy properties there?
I think that's important. I don't know. Well, we need to observe them.
No one.
I think that's, I mean, I think really is the picture of my impression is at those high redshifts, these are such a stream system, they're just very large scatter. At some point, you have to get back to the MC relation at redshift 0. Exactly when that happened is really interesting. How these things get settled down to it. You have to go to lower redshift to see when that happened.
Right, but they are so rare. I mean, when you say they are even unobservable in the nearby local volume, then we don't see those outliers anyway, right?
Correct. Yeah.
Do you, in your group, do you have time on the Euclid instruments? Or are you working with that?
Well, I mean, Euclid is a survey, so everybody get their data. So I'm involved in the high redshift enterprise in Euclid, and so we'll be start observing as soon as data come in. We'll try to start looking for quasars.
Okay, so that will be an actual new search.
Yeah, that will be the next. That's the natural next step. The next big step is when Euclid collects sufficient number of quasars, whether we can go to redshift 8 and beyond. I think I'm sure there will. I mean, how hard it is, I don't know, but because at those redshifts, the contaminants is really bad. We are really talking about looking for many dozens of objects to find one of these red 7 quasars. I don't know how clean the Euclid selection will be. We'll see when the data comes in.
I was hoping for a preview, but that's all right.
They haven't started talking about science data yet, so.
I Liam and then looking at it.
Would you mind going to the slide for the 3 sort of categories in the ALMA data? Yeah, so I hope you'll forgive a naive question here. For the rotating disk type case, is that implying that we're looking at sort of a face-on disk? Or I wanted to see if my physical.
Oh, this is not quite face-on. I mean, face-on you will not see the rotation.
Well, you're right, yes.
Yeah, I was looking at this, yeah.
Yes, but not
the disk.
closer to face on than edge on.
For this particular, yeah, look pretty round.
Yeah, okay. That's it.
But yeah.
Okay.
You're talking about contaminants in Jupiter, like roughly how many you have to sift through to find the redshift 7 sources? And I assume they're mostly like dwarf stars or.
So it's a hard, I mean, it depends on how hard you want to push. I think for redshift sort of 6.5 to 7, I mean, if you push towards sort of the metric limit, then the contaminant just rise to the wall. It just like completely overwhelm you. So it's sort of how much teletime do you want to burn to just go to another 0.1 magnet finger to find the highest redshift objects. For redshift 6.5 to 7, it's not that bad. You can make it down to like your success rate will be 1 out of 2 or 3. As soon as I get the redshift 7 for ground-based data, as I said, just a wall of contaminant come in because things are rare and you're pushing the limit. So the few redshift 7 objects we discovered, we're going through 100 to find like 10, for example. It's like a few percent of rate, but that's sort of almost by design because we don't have better thing to do. Hopefully, and then that will be a problem with Euclid because Euclid have good infrared data, but whether their optical data is good enough to do this work is not quite clear to me.
The contaminants is noise or is
A combination. I mean, so they are depending on the redshift and the luminosity range. On the brighter end is mostly cool dwarfs, like LT dwarfs. On the fainter end, probably a lot of compact galaxies. The cool dwarfs just because their colors are, especially the most annoying things are like a late L, early T dwarf. Their color just looks similar to quasars in broadband, and there's nothing we can do very much about it. You just have to accept they're more brown dwarfs than quasars at the bright end. For when you go to fainter, it's mostly just like a 2 sigma scatter from a lot of the red things in the universe. And there are plenty of compact galaxy redshift 1, that's cool.
Since you said the optical was going to be a challenge in Euclid, why isn't it practical to just wait for the first year of LSST and the first deep pulse test?
They're not patient.
Yeah, that's better.
I'm sure people are gonna try.
Sure.
As soon as data come in, to try to see what, I mean, actually, early time is not to even to discover something, it's just to figure out whether we understand the data or not. I mean, to find rare object is a very efficient way of debug the sort of the photometric, the data reduction actually.
Other questions we heard? If not, let's thank our speaker. So, 2 announcements. If you'd like to have dinner with our speaker, we'll meet outside in the lobby around 5:15 or so, and go from there. That gives people a little bit of time to head home, pick up kids, and meet us later.